All right, folks. So yesterday we had a quick bit of revision about Hess's law and Hess cycles, okay? And then I started to introduce the idea of what a new entropy change was. What was the new entropy change that I talked about? Huh? Lattice energy, exactly, okay? So what we're going to do, and this will take a while to build up together, but we're going to build what we call a Born-Haber cycle this morning, okay? I've started it on the whiteboard over there. Let me take this thing off about the early atmosphere. It doesn't distract you. So I've started to build it a little over here already, okay? We already know a little bit about these entropy changes that I've put in, okay? We're going to make a Born-Haber cycle, well, probably the most simple one that I can think of, which is for sodium chloride, okay? So I've got two entropy changes I've put in already, okay? Here I've got gaseous ions forming the ionic solid, okay? So if it's gaseous ions to form the ionic solid, what kind of entropy change is that from there to there? Huh?
Negative.
It is negative, yeah, but what did we call it? What was the actual name of that entropy change? We just defined it yesterday, I think.
Bond. No, not bond energy.
Not bond energy, quite, no.
Lattice.
Huh? Lattice. Yes, it's the lattice entropy or the lattice energy. It's exactly what we defined yesterday. Okay? So that's our entropy change lattice. Okay? This one down here. Okay? If I go from the elements, they look like they're in their standard state to me, to a compound, so elements to a compound, what kind of entropy change is that? You've defined that before as well. See that? Formation is an entropy change of formation, isn't it? Okay. So that's an entropy change of formation. Now, to be able to work this out, this lattice energy, I need an alternative route to get all the way around here. Okay? If I can go all the way from here to here, then I can work this out. Okay? And there's lots of, 3 or 4 different entropy changes that we need to go from this to this. Okay? And they all happen in a particular order to make sense. Okay? And you can hopefully start to tell by the difference in the charges, by the difference in the states, okay, whether they're joined up as molecules or not joined up as molecules, okay. So we're going to work through this. We're going to try and define each entropy change as we go, okay, and you'll be able to hopefully by the end of the lesson do your own little Born-Haber cycle as well and draw one, okay. That's our aim for the lesson. If you can draw a Born-Haber cycle by the end, you would have done very well. All right. So, first step. I'm going to be quite little stages here. Okay, we're going to build it up step by step. So, I want to ask you first, what change might you make first to this? So I want to be able to change this slowly into this. And there's going to be different stages of it. Okay, what might make sense to do first? Ahmed?
Possibly have it as, like, instead of half, have it as Na plus E minus plus Cl.
That sounds like a more than one change at once. Okay, I want one thing, one step. Okay, don't try and jump through lots of different things. Okay, what could I change? Just a simple change first. Leanne?
Maybe making Cl. I was going to say thermal decomposing it and get it into. That was right.
Go on, no, carry on. What were you saying? It's fine.
Thermal decomposition. I wanted to decompose it.
Which one?
Na.
Na. Okay, so what are you going to change it into?
remove one electron and make it into Na.
Okay, we're removing one electron to make it into Na+. I do need to do that. But I want you to go back just for a second. You might want to remember what is the definition of ionization energy. That goes back to like topic 1. James, do you know?
Put sodium into gaseous state.
Okay, we are going to do that. That is going to be first, okay? But I just want to see if I can answer the other question. When it comes to ionization energy, how is that defined? Does anyone actually remember? Okay, yeah, but so 1 mole of each, that's going to come in there somewhere, but just thinking specifically about ionization energy.
The entropy required to remove 1 electron from a 1 mole gaseous state.
Okay, so you got it there. So it's the energy required to remove 1 mole of electrons from 1 mole of atoms in their gaseous state. Okay, I can't ionize it before it's a gas. Okay, so the first thing I want to do, and James, you're absolutely right, I wasn't trying to say that you were wrong, possibly the first thing to do is to get sodium and turn it into a gas. I haven't done anything to the chlorine yet, so I'm going to keep that exactly the same. This, and we will write definitions for these later, but this is called the enthalpy change of atomization. And in particular, that one is for sodium. Okay? Atomization is the enthalpy change when we change 1 mole of the element in its standard state into 1 mole of gaseous atoms.
Does it kind of like go up, like all the way up?
Yeah, it's going to keep going up.
Like until that?
It's going to go a bit further than that one, actually. Okay, so there's another one. The size of the arrows in between doesn't necessarily matter that much. Okay, so I know that I've already got Na gas. I'm going to give you that much. So I'm not changing the sodium. What will I need to do next? The moment I've got half Cl2, what do I want to change that half Cl2 to?
To Cl.
Just to Cl. Okay, I want to break apart the molecules and just make them atoms. Okay, and there's an enthalpy change with that as well. So the change is taking half Cl2 and changing it to Cl. Okay, that is also atomization. So that's the atomization for Cl.
But what happens if I was to remove it, like make it into gases and then it was to make it only Cl? Like, what happens physically?
Physically, what will happen?
Obviously, it'll turn to gas, but what is it they do? Kind of.
Well, to turn sodium from a solid into a gas, you need to heat it up. So you need to give it energy. And that's why there's an entropy change with that. And similarly to break apart chlorine molecules into chlorine atoms, you need to give them energy. And they will, and the energy will break the bonds, yeah? Most of this can be done with heat, really. Okay? Alright, so we've changed from the elements in their standard states to the atoms in the gaseous state. Okay, there's actually only 2 more steps to this. Not that bad. Okay. I'll give us a little clue as well. 1 is going to go down like that. The other one is going to go up. Okay? So, there are 2 things that we need to do. You may not get them in the right order, and that's okay. But what is one of the things we need to do? Go on.
Remove 1 electron from sodium.
Okay, remove 1 electron from sodium. Yeah? If we move 1 electron from sodium, that is actually the one that goes in there, here. Okay, so you're actually right. So we're going to go from Na gas to Na plus gas. And the CO is still the same. Okay. And we know that the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state, what have I just defined there? What do we call that?
First ionization.
Yeah, ionization energy, or in this case, because it's the first one, it's the first ionization energy. Okay? So this one is ionization, IE1 for sodium. Okay? And we don't need to go further than that, there's just one ionization energy. And the final one, we've already got the arrow in. Okay? And the change, or what's the change that we're making?
HCl to an ion.
Okay, so changing the chlorine atom to a chlorine ion. What do we actually have to do to change chlorine atoms into chlorine ions? Add an electron, exactly. Yeah, because it's going from a neutral atom to a negative ion, okay? This is one of the new ones, okay? I've just talked about what atomization is, okay? This enthalpy change is electron affinity. And I'm just going to put it in there, EA. It's the EA for chlorine, okay?
So I have a question.
Yeah.
Should we, for sodium, when you remove an electron, do you write it?
You can write it if you want, you don't have to.
Okay.
Yeah, you could write plus E minus here
Yeah.
if you wanted to. I don't tend to when I draw them, and it's absolutely fine not to. Okay, but if it makes more sense to you, then that's okay.
All right.
Okay, now we've got everything filled in. So essentially we're doing like a big head cycle here. Because the enthalpy change from here to here, the enthalpy change of formation, is exactly the same as going all the way around here, around the cycle. Yeah? So the enthalpy change of formation is equal to and I'm going with the arrow all the time as well. So the enthalpy change of formation is equal to atomization of sodium plus atomization of chlorine plus ionization energy of sodium plus the electron affinity of chlorine plus the lattice energy. Okay? And it's just like a really big extended head cycle. That's all. Okay, so it's a little bit more complicated when we do head cycles with lovely covalent compounds.
So,
Go on.
When we go against it, would it also apply the same rules?
So if we have to go against an arrow, then we have to change the sign.
Okay.
Okay? Because you could say, if you're trying to work out the lattice enthalpy, this change here is equal to minus this, minus this, minus this, minus this, plus this. Yeah, you can start from any point on the cycle and go around in the other direction, yeah, to get the particular enthalpy change. Okay, so if I was going to write wonderful equation for this, it looks horrible, it's not that bad, but the enthalpy change of formation in this case equals delta H of atomization for sodium plus, it's going to get quite long this, delta H of atomization for Cl plus the ionization energy, number 1 for sodium, plus the electron affinity for chlorine. Oh, and I've got to go to another line, plus the lattice enthalpy. Okay? I don't know, I mean, hopefully what you see here is actually the building of the cycle is not necessarily that difficult. However, and even writing this out is probably not that difficult. It looks horrible, but it, you know, because there's lots of different symbols and letters in it. But when you actually do this calculation, there's a lot of points for error. There's a lot of places where you can make mistakes, because some of these are going to be positive numbers, some are going to be negative. Okay, you need to put everything incorrect into your calculation. Okay, when it actually comes to doing a calculation, that is. Go on.
So I have a quick question. So why does it need standard? Like, what does it need entropy change of atomization from half Cl2 to Cl? But isn't it the same thing?
Not, no. Because half Cl2 means you've got half a mole of chlorine molecules. Yeah? Whereas going to Cl gas means you've got 1 mole of Cl atoms. So they've been broken apart. There's no covalent bonds between them anymore. Yeah? That's okay. Is there any other questions looking at that? Anything else that you like? What are you talking about, sir? What kind of craziness is this in my life? No one's asking. Excellent. All right, so your task then. Before we start doing any calculations with this, okay, I want you to see if we can extend this. Which one are we going to do? We'll make it a tiny bit more difficult for you. Put it in here. I don't want to rub it all out. So I want you to draw a cycle for MgO, magnesium oxide. Now hopefully the first thing that occurs to you in that is, oh hang on, I've got to make Mg2 plus and O2 minus. So not only do I need, well, there's a first ionization energy, but there's also a second one as well. Okay? So I'm going to give you a few minutes to see how you do with that. Okay? So I think most of you have done your own cycle now. And the difference was, to do MgO, you needed to obviously first do the atomization steps. That should be exactly the same. So you need to go from Mg solid to Mg gas, and then half O2 to O gas. Okay? Then you did 2 ionization energies for magnesium, so from Mg to Mg plus, and then Mg plus to Mg2 plus. Okay? And then with oxygen, you need to do 2 electron affinities. So you go from O to O minus, and then O minus to O2 minus. Okay? So there's a couple of extra steps in the cycle for magnesium. Okay? What I think we should do, and what I think we should have written down properly in our books, are definitions for the 2 new things here, the atomization and the electron affinity. Okay? So we'll take this off, put in some definitions. Yeah? Electron affinity. So, we'll have definition.
Okay, polarization's okay. Like there's 3 steps you have to say. Like, transverse wave. Like there's 3 types of questions. They can either say why sound waves or like explain what polarization is. It's all not bad. And then refraction, it's like either a calculation or the definition or like I don't like those either. But if you just think about it, if it's bigger than 90 degrees, then it's just gonna like
Okay, so entropy change of atomization, folks. The definition. So it's the entropy change when 1 mole of gaseous atoms is formed from elements in their standard states under standard conditions. Okay, and that's important that it's 1 mole of gaseous atoms formed. It's not necessarily taking 1 mole of the element in its standard state. We want to form 1 mole of gaseous atoms. You definitely need that definition if you've not done so already. One thing, we've never really talked about this, probably because I haven't taught you the topics before, but standard conditions. What are standard conditions? You should know. Jemima, you were telling me one just then. Okay, so it's 101 kilopascals. Good. That's one.
298 Kelvin.
298 Kelvin. Okay. Anything else? Not that it's necessarily relevant for this, but another standard condition that is important is that if you've got solutions, they're always 1 mole per decimeter cubed. Okay. That becomes very important in one of your topics you do with Mr. Collins this year. Okay, with solutions. So that's entropy change of atomization. The other one is electron affinity. So delta H standard EA, and that is I might just change that a second. Almost forgot a word there, didn't I? Almost forgot gaseous. But electron affinity says the entropy change when 1 mole of electrons is added to 1 mole of a gaseous species under standard conditions. I put in species rather than saying a gaseous element or a gaseous ion because it could start as a neutral atom or it could be a negative already. Okay, so it could be an atom or an ion, which is why I've just used species instead. Okay. One thing as well to add to that about electron affinity, which is quite interesting. And it wouldn't have mattered the way you drew your cycles at all because the arrows are going in the right direction. But the first electron affinity for anything, if it can allow electrons to be added to it, is always negative. It's always exothermic. But the second, or even a third, if possible, is always positive. It's always endothermic, which is interesting. Yeah. So the first electron affinity is exothermic, but the second one is endothermic. I wonder if anyone can work out why that might be.
So
Use your.
the first one's.
So the first one, it gives out energy, but the second or a third would always take in energy. It would need energy to make it happen. I see why you might say that, but usually if we're adding in electrons, they're going to be in the same shell. It's going to be usually to fill up the outer shell. James?
After a second electron, it would create a pair.
After a second electron, it would have created a pair. I see your point. That's quite a good way of looking at it. It's not right, but it's quite a nice way to look at it. Actually, they'd probably, each time you have to put one in, it would be creating a pair in an orbital anyway.
Is it because of the interface attraction between the nucleus and the electron? Because as it
No, I like that though as well. Now you're really starting to think about it. Let me put something up. In fact, if I just write the equations for them. So if you have the first electron affinity for oxygen, let's say, that's going to go to O minus. This is the second electron affinity. Okay, so O plus E minus to make O minus, that's our first. O minus plus E minus to make O2 minus. The answer is actually staring at you in that second equation. Ahmed.
Well, I mean, oxygens become minus, so when you're adding another electron, is it because they're
You're almost there. You are so close to it.
is it because they can't, so they push it away?
Right, okay. Well, they push it away. Well,
They repel.
exactly, okay? The second one is it's already you're trying to force an electron into something that's already negative. They repel each other. So you need to put energy in to force it in there.
But why is it? Oh, is it because you're adding like energy to it?
You need to give it energy to force it into
Okay.
that, okay? So the note I was trying to make, okay, was that second electron affinity always positive because of repulsion. I won't go any further than that. You could probably add a few more words in there if you want, but I'm not going to add any more words into my notes for you. It's there. It's in the equation. Okay. So there's some interesting stuff going on already today. So you've already been able to draw your own Born-Haber cycle. Okay, we've got new definitions for entropy change of atomization, definition of electron affinity. We've looked at why second electron affinity is always positive or always endothermic. Okay, that's a massive amount of new learning. But we want more than that. We need more than that. It's pretty noisy. So what I want to do is be able to give you an example, but I know you haven't got this textbook. That's better. So going to have to find you some numbers from my textbook. What's wrong with that?
Why is the first one extra zero?
Because if it's able to, if an electron is able to be added, then there's actually a certain amount of attraction that is there, and therefore it releases energy. Yeah? But the repulsion makes it alright, so you're going to go back and look at, don't know why I'm using that, you're going to go back and look at your cycle for sodium chloride that I put up originally. Okay, and we're going to just stick some numbers in, see if we can work anything out. So,
No, I just said what do you mean you're right? I'm not. It's not straight.
Okay, folks, so that should be all the numbers you need. What I want you to work out is, using the Born-Haber cycle from the very start of the lesson, I want you to be able to work out the lattice entropy or the lattice energy for sodium chloride. So you've got formation, you've got all the atomization, you've got ionization energy and electron affinity, and that should be enough to be able to work it out. Plug the numbers in, away you go. Okay.